Okay, welcome. This is the first video for the acceleration and friction unit. This is the unit where we're going to start bringing things together, bringing together ideas like force, um, equilibrium, force diagrams. We're going to start using these to help us solve problems. Okay, so for this unit, I want you to be able to understand the models for static and kinetic friction. I want you to be able to calculate acceleration from the net force. And I want you to be able to solve problems involving the modified Atwood's machine. Okay, let's go and get started. Friction. It's basically a force that opposes sliding. So that means that it has to be a force that's parallel to the contact surface. And basically, what we can think about friction doing is it's going to convert mechanical energy into thermal energy. So if you imagine taking your hands and sliding them back and forth, your hands are going to warm up. That's because the friction is converting your mechanical energy into thermal energy. And friction always opposes sliding. That's very important that we say that. It opposes sliding. On a microscopic level, we see that there are all these little tiny peaks and valleys between two surfaces. So one model for friction is that when two surfaces are in contact, the peaks and valleys line up. And that causes the friction. Another model is to take a look at the atoms. And we know that there are London or van der Waals forces that hold molecules together to form large structures. So in some way, the molecules will be attracted to each other between the two surfaces. Now, for static friction, what we have to understand is that it's still an open level or open area of research. We're getting better and better models, but we're still creating models. In a simplified model, what we're going to look at is the maximum static friction that can occur between two surfaces. And the model for that is the fact that this maximum static friction, so I've got maximum for max and S for static, is going to be proportional to the normal force that we've talked about before. Remember that the word normal means perpendicular, so that's very important. So since we have proportionality, we need to have a constant of proportionality. For us, that's going to be mu. It's this little letter right here, and it is the coefficient for static friction. So the maximum static friction that can exist will equal the coefficient of static friction multiplied by the normal force. And these are vectors. From experience, you may understand that it's harder to get something to slide than it is to keep it sliding. So if we were to make a graph of the friction forces, which is on the y-axis here, versus the applied force, which is on the x-axis, what we would see is that as we push on an object, the static friction becomes stronger. It's a changing force. There is a breaking point. Up here at the peak of this graph, this is our maximum static friction. At this point, the object will break free and it'll begin to slide. Well, when it's sliding, we call that kinetic friction. That's where we're pushing something, there's still friction, it's still opposing sliding, but the object's moving. And notice that this level of kinetic friction is lower than that level for the static friction, the maximum static friction. In this force, the kinetic friction force is a constant force. It does not change. Static friction does change. So we need to be able to calculate kinetic friction. Well, Um, this one's actually a lot easier. Well, I hate to say easier. It's actually very much the same. Kinetic friction equals the coefficient for kinetic friction times the normal force. That's really all there is to it. The coefficient for static friction will always be greater than the coefficient for kinetic friction. Also, it's unitless. If we take a look at, friction equals the coefficient times the normal force, we can see that the coefficient will always be friction divided by the normal force. So the coefficient is a ratio between the friction to the normal force. So it is unitless. All right, let's take a look at an example here. If you're ever to go to San Diego, or yeah, for sure, yeah, it's San Diego, or really any city where there's a lot of hills, cars tend to be parked on a hill. Well, one thing I would like to know, what's the steepest angle that can exist between that this car can be parked on before it just starts to slide down the hill, regardless of how much friction there is between it. To answer this, we have to start with a free body diagram. So looking at the forces on this car, we know that there's going to be a gravitational force acting on the car. We know there's going to be a normal force towards the front of the car because it's on a hill. And what we're interested in is the maximum static friction between the tires and the road. So if I were to put these forces on this diagram, here's my normal force, here's my maximum static friction, and here is the force due to gravity, and the angle of the hill, or the incline, will be the same as that angle right there. Okay, so looking at this, we see that the gravitational vector can be resolved into its x and y components, where fgx would equal fg times sine of theta, or I could say mg sine theta, and fgy would equal fg cosine theta, or mg cosine theta. Now, to help us answer this, what is theta going to be? What is the maximum that theta can be? We need to go back and study the forces along the x and y axes, and we need to remember equilibrium. Basically, the sum of forces on the y-axis, which is the normal force minus fgy, that needs to equal 0 because we want equilibrium on the y-axis. So going through here, the normal force minus, now fgy, we just got done saying, is mg cosine theta. Equals 0. So in other words, the normal force equals mg cosine theta. So that's the first equation we would need. Then we need to take a look at the forces on the x-axis. Well, on the x-axis we have our fgx trying to pull the car down the hill, minus the maximum static friction trying to keep the car from sliding. And again, we want equilibrium. We want this car to stay put. So the sum of those forces need to be 0 as well. All right, well, we can go ahead and start plugging some things in. Fgx, well, that's going to be mg sine theta. Our model for friction is the coefficient times the normal force, and that has to equal 0. Okay, well, from the y-axis, we know what we need to plug in for the normal force. That's right here. So we're going to take that, plug it in right there. So we're left with, I'm going to also add the mu and normal force across. There we have it. Now we can do some algebra. Doesn't matter how massive the car is. It doesn't matter what planet we're on. You know, we're left with sine theta equals US cosine theta. Okay, well, we can now divide both sides by cosine. And sine divided by cosine is tangent. And there we have it. This maximum angle would equal the inverse tangent of the coefficient of static friction. Likewise, we can use this formula as a way to measure the coefficient of static friction between two objects. We would need to put an object on a ramp so that we know the two surfaces, and then simply adjust the angle until it begins to slide, and that would tell us U sub s. It would give us the coefficient between the two surfaces. All right, well, that wraps up this video. We'll finish this off in video number 2.